All right, good afternoon. Everybody have a good lunch? Really excited about being here. Okay, I sent an email yesterday reminding all of you of what's coming up. There's only 2 weeks left in the quarter. Yay. But also, for those of us that are behind, that's a deadline, okay? You got to get busy and got to get stuff knocked out here, okay? So don't get far behind here. Looks like several things this week, okay? And there kind of is quite a few things going on this week. But you won't have any FRQs next week, okay? So if you need to push one or two of those to next week, that's your decision on that. But let me just remind you of something, okay? Several of you already decided I'm not going to look at the FRQs at all this week. Remember that next week is Spirit Week. You're not going to want to look at anything next week. You've also got a test next week in here, so don't push it off thinking I'll get it done unless you really are planning on committing some time to it there, okay? But that's our schedule for the next couple of weeks. We'll have a test next week in there. Today, we're going to be talking about 14, which is natural logarithms. You learned about logarithms last year. You learned about them probably even in Algebra 2. You probably learned that you didn't like them, would be my guess. That's what most students have. We will deal with logarithms, and believe it or not, by the end of the day, I'm going to show you how a logarithm can sometimes make things easier for you in calculus by actually throwing logarithms in there. So lots of important things here. We will predominantly use the natural logs. Now, these are things that you should already know. Don't freak out if you don't remember them, okay? Because if you don't use them a lot, they kind of go away from you. This side, the left side, is saying the same thing as the right side does. But we will predominantly be using the LN, the natural log, because we use LNs and E's quite a bit. The things that you need to be certain that you memorize and know are these things right here. The first three and the last three. Those are the ones you're going to use more often than anything. This is just the definition. This first one is just the definition of what a log is. Natural log says the base e to the y power equals the argument x. And you're going to hear me use that term argument quite a bit. Anything inside the parentheses on a log function, inside the parentheses on the, come on in if you need to. It is, but he's probably in his office down the hall there.
Okay, thank you.
Anything, any trig functions, anything inside a square root, I'm going to refer to that as the argument quite often. So the argument is inside here. So the definition says e to the power of y equals the argument x there. Do you remember these powers, specifically these last three, that if you're taking the natural log of two things that are being multiplied, you can split it up, the natural log of the first thing plus the natural log of the second, dividing and subtracting, and then the natural log of something to a power, you can bring that power down and make it into the coefficient in front of it. So those are just things you're going to have to use. We're going to look at a few examples and see if you remember how to use these principles, use these properties of logarithms and expand things out. Down at the bottom here, just a few things that you need to be sure you know. The domain is positive real numbers. What does that mean? That means the argument has to be a positive real number. The argument can't be 0. So I can't take the natural log of 0. I can't take the natural log of a negative number. So the domain is all positive real numbers. The range is all real numbers. The domain is positive. The range is all real numbers. The functions continuous and the other things we'll talk about later on. But those are the two things you should know right now or be committing to memory. Domain is all positive reals. Range is all reals. So let's look at the properties. This is not calculus, okay? This is just going back to stuff that you studied in Algebra 2 and you studied last year in college algebra. How do we expand this out? ln of xy divided by z squared. So I want it to written as a series of things with pluses and minuses between them. We're adding and subtracting, and just one thing inside the argument each time.
ln x plus ln y minus ln of z squared.
Okay? What do you think, class? Okay? That's right. Nothing wrong with what he's got here. The plus sign, because the x and y are being multiplied on top. The minus sign, because we're dividing. He said z squared, but as Mr. Butt said, we could actually simplify that even more and make it ln of y minus 2 times the ln of z. So that would be considered the expanded form of it. Sometimes you're going to have to be able to expand things out like that. Does this bring back memories, maybe even bad memories from previous math, but it's something you've seen before. Let's look at another example. What about the ln of the square root of 5x minus 6? We could think of this as 5x minus 6 to the 1/2 power. So we could easily write it as 1/2 ln 5x minus 6. And this is where a question arises. Can I simplify that 5x minus 6 any with my logarithmic properties? If you go back and look at your log properties, there's not one with a subtraction sign inside the parentheses. So this is as simple as that can be, or that's the most expanding we can do on a problem like that there. We can't separate this out by the minus sign into ln of 5x and plus or minus the ln of 6. It doesn't work that way, only if it's dividing. So this is one that students mess up on, is they'll want to expand that out further. That's the most we can do to expand something like that. All right? Do y'all remember doing this before? Y'all seen this stuff before? Okay. Y'all remember, is it relatively easy for you to do this? Okay. So expand that out right quick, and then we'll move on and do some actual calculus here in a few minutes. Because we're multiplying two things on the top, we're dividing by something on the bottom, so it's the ln of 3 plus the ln of x minus the ln of 4. Yeah, we're going to get there. Now, believe it or not, when you look at the next one, the fact that this has an ln in it actually would make this problem easier in calculus than harder. Okay, you've got a lot of things going on here. Notice in the denominator, or just for clarification, this is x times the cube root of x squared plus 1 in the denominator. It's not x cubed times the square root of x plus 1. It's x times the cube root of x plus 1. There's a common mistake students will make here, so be careful as you're trying to expand this out. Why do I have two minus signs there? Am I wrong? Why the two minus signs there? Okay. What's happening? We're multiplying, but we're multiplying two things in the bottom. Okay, so if you were to go the long way with this, this is the ln of x squared minus 5 squared minus the ln of x times the cube root of x squared plus 1. Now, when you split up this second term right here, you split it up as ln of x plus the ln of the cube root of x squared plus 1. But there was a minus sign in front of all of this. So we've got to distribute that minus sign through. That's how I got the two minus signs there. So you should have a minus sign in front of the ln of x and a minus sign in front of the last term because they were being multiplied together originally in the denominator. Common mistake would be to put a minus sign in front of the ln of x and not put a minus sign in front of the last one, put a plus sign, or only have the one minus sign there. Well, you're never going to be asked to do what we just did in this class, okay? I'm never going to say, give you a problem, say, here, expand that out. But all of these are strategies that you may need to use in order to find derivatives that we're about to get into. Well, what is the derivative of the natural log? Now we're starting calculus. The derivative of the natural log is 1 over the argument. So if the derivative of ln of x is 1 over x. Now, what does it mean that that's the derivative? The derivative is the what as far as on the graph? What are we looking at? The slope is the rate of change. So remember, that's what we're talking about. The slope is the rate of change. Now, what if it's something other than x in there? Like several of them we've already listed out. We had the ln of x squared plus 1 or the ln of something like that. That's what I've got written over here. If the argument is something other than x, okay, it's 1 over the argument times the derivative of the argument, or the derivative of the argument over the argument itself. That's the reason I've got the prime up there on u. So this is just another function, another definition of derivative that you've got to remember. ln of u is 1 over u times u prime. 1 over the argument times the derivative of the argument. That's all the calculus we get to learn today. Let's see if we can put it into practice. So what's the ln? What's the derivative with respect to x of ln of 2x? Well, we just said it's 1 over the argument, 2x, times, what's the derivative of the argument? 2, which simplifies just down to 1 over x. Would you agree? Some of you say, wait a minute, why didn't you expand that out? Good question. I could have taken ln of 2x and said, well, that's the same as the ln of 2 plus the ln of x, couldn't I? Well, what's the derivative with respect to x of that? What's the derivative of ln of 2? 0. Why? Yes, ln of 2 is just a number. It's not a pretty number, but it's just a number. So that would become 0 plus the derivative of ln of x is 1 over x. So whether you do it this way and use the chain rule, or whether you expanded it out, lo and behold, we get to the same answer. Math's still right. 1 over x. So, which way do you want to do it? I don't care which way you do it, okay? After you've done a few hundred of these, it gets real easy. You'll be able to look at it and tell me that's the answer. Poof, write it down. But the answer for derivative of ln of 2x is 1 over x. Questions, comments, observations? All right? Let's get a little bit more challenging. Derivative of x, ln of x. When I was grading homework last night, I noticed several of you were making what I would say is a common mistake with something like this. Tell me, what's happening between the x on the outside and the ln of x there? They're being multiplied. What is that? That should trigger something when you're talking derivative.
Oh, 1.
Yeah, a little bit more than that. I've got to take the derivative and things are being multiplied. Product rule. Some of you didn't trigger when you were doing that homework. Product rule. Okay? Talk yourself through it, okay? First, x times, what's the derivative of ln of x? 1 over x. Plus, second, ln of x times derivative of first, 1. So, this first term right here becomes the number 1 plus ln of x. 1 plus ln of x. A little bit more complicated looking than what we started off with there. Does everybody understand how to get to that, though? We've got to use a product rule there. Your product rule doesn't go away just because we're learning something new. Quotient rule doesn't disappear just because we don't like it. It has to still be used. Questions about this problem? Good. Let's get more challenging then. ln of x cubed plus 1. Take a moment, see what you can come up with for a solution there. Then we'll discuss it. The derivative of ln is 1 over the argument times the derivative of the argument. I get 3x squared over x cubed plus 1. Why can't I cancel out the x squared and the x cubed and just get 3 over x plus 1? Huh? Yes, they are. Because of the plus 1 in the denominator. The fact that if they're both monomials, I could cancel. But I've got 2 terms in the denominator. I cannot cancel out there. Another common thing that students like to try to do is cancel stuff out to make it look easier. What's being squared?
Is it the logarithmic function?
The logarithmic function itself is being squared here. So how do you need to take this derivative? Chain rule. What's your inside function here? Right. Inside is ln of x, and outside is something being squared. So take a moment and struggle with that and see what you can come up with for a solution. So my outside function is something being squared. So I'm going to say it's 2 times the ln of x to the first power times, what's the derivative of ln of x? 1 over x. So we could simplify that to just being 2 ln of x over x. 2 ln of x over x. You could even write it as ln of x squared over x. Now, how did I do that? Right. Because when you're dealing with logarithms, by the logarithm properties, I can take the coefficient right here and make it into a power. That's what I did. Either of those is an acceptable answer. You need to be able to recognize both of them because either one of them might be on the test. All right, questions, comments, observations? Easy, hard, confusing, boring? All of the above. All right? Differentiate. So, take a moment to solve that problem. Let me see how many more of these I'm going to throw at you before I get real hard. You go ahead and be looking at that one. I'm only going to throw a couple more at you. I think this is far easier if you start off by using your properties to pull that 1/2 out in front. If you don't, it's doable. You just have a chain rule inside of a chain rule inside of the LN. So I would start off by pulling my power of the 1/2 power designated by the square root, pull it out in front of the LN, then take the square root, then take the derivative of it. Do I need to use the product rule because I have 1/2 times Ln? No, why not? It's a constant number out there. Very good, very good. So I just know my answer is going to have 1/2. Then I take the derivative of Ln of 3x minus 5, which is 1 over 3x minus 5 times the derivative of 3x minus 5 is 3. So suddenly, I think that would be the correct answer for my derivative, 3 over 2 parentheses 3x minus 5. And just think about all of the application type problems we've done, where find out where it has horizontal tangent lines, find out where it has vertical tangent lines. We can do all of that fun stuff with this stuff too. We can write the equation of the line tangent to the function at x equals whatever. Wow, so much fun we can have here. You just thought you were having fun already. Okay? I know we've been kind of beating this to death, but look at that mess right there. Now, what do you think you should do to begin with on a problem like this if you're supposed to find the derivative? Try is an option, but it doesn't really help you get to the answer very well. Split this thing up. This is where utilizing the properties comes into play. Because just think about if you say, oh, I'm just going to take the derivative like it is. Well, it's 1 over the argument. That's ugly enough. But now take the derivative of this argument. Well, I've got a quotient rule, don't I? But then also in the top, I've got a power rule. I've got a product rule. Whoops. I've also got a chain rule in the top, and I've got a chain rule in the bottom. You're going to go crazy trying to get the derivative of that thing if you try to do it like it is written there, okay? Split it out to begin with before you ever start doing anything. Now, notice that I've got written f of x equals that. A couple of you have been stating that incorrectly. I haven't taken a derivative yet. So it's wrong for me to put f prime right here. That is not f prime. That is just the function. We haven't done any calculus yet. Now is when we can come in and do some calculus. Now we can find the derivative. The first one is easy. We know it's going to have a 3, 1 over the argument times 2x. Boy, that was easy. Minus, we know it's going to have a 1/2, 1 over the argument times and provided we don't have to get a common denominator and write that as one fraction, that was a relatively easy problem, wasn't it? Okay? So, that would be simple. You could get the common denominators and you could add that stuff together. You wouldn't like me very much if you had to do that, but you could do that. It would be a process for you. Any questions? Now, I want to show you, we're not going to look at this last problem. We're just not going there. But I want to show you how this can help you. Suppose you have a problem like this. Y equals x squared plus 3 to the 4 over the square root of 2x plus 7. And I said take the derivative of that. Okay? Now, look at the mess you've got on the right-hand side. Think about trying to take the derivative of that right-hand side. You've got a quotient rule. You've got a product rule in the top. But inside the product rule in the top, you've got a chain rule to do. That's going to be an absolute mess to work with. Would you agree with that? Now, what if we were to take the natural log of both sides to begin with? Okay? We introduced natural log on both sides. So we haven't changed the problem. Okay? Now, why would I do that? How does that help us? Can anyone tell me? Why so? Suddenly, look at what we can do on the right-hand side. We can take this right-hand side now, and we can write it as 2 ln of x plus 4 ln of x squared plus 3 minus 1/2 ln of 2x plus 7, can't we? Well, that's much easier to take the derivative of. But now, I got to take the derivative of the left side now, though. What's the derivative of ln of y? Almost. Very good. 1 over the argument, 1 over y, times y prime. That makes sense? And then the derivative of 2 ln of x is 2 over x plus 4 times 1 over x squared plus 3 times 2x minus 1/2 times 1 over 2x plus 7 times 2. Suddenly, that was a lot easier to do than that original problem I gave you. Much easier to deal with. But we still got this 1 over y in there. I want y prime by itself.
You plug in more y.
Very good. Both of you are right. You can multiply both sides by y, because if we multiply that by y and this by y, that gets rid of it. But if we don't want y in the equation, what do we know that y is equal to? Y is equal to this mess up here to begin with. So I'm not about to tell you that it's easy, but suddenly we've got this 8x over x squared plus 3 minus 1 over 2x plus 7, all times this original thing up here, x squared plus 3 to the 4th over the square root of 2x plus 7. Now, I'm not saying by a long shot it's easy, but I promise you it's easier than taking the derivative of the first thing we had. And it's the same answer in the end. Absolute same answer. So, sometimes you will see, how will I know to do something like this? First of all, it's probably going to look ugly like that. But on the web assignment that you've got assigned to you for next week, you'll see it say use logarithmic differentiation. That's a fancy way of saying put a log in on both sides, and then you can use your logarithmic powers on it. Logarithmic properties, not powers. They're not superpowers. Okay. Questions over taking the derivatives of natural logs? All right. You have a homework tonight. You have a web assign tomorrow. I know a web assign maybe Wednesday. I don't know. You've got a web assign sometime too. You've got FRQs, and you've got this homework you can be working on. So plenty of things you can be working on for the next hour and a half if you so choose to. Please choose to.